So we have written the truth table, and from the truth table we have written the K-map, and from the K-map we have also derived all these expressions, right? So this is how you are getting the expressions from the K-map. Okay. So now by just looking into these expressions, that is G3 is equals to B3, we shall write the circuit diagram. So what is G3? G3 is nothing but B3. Okay, there is no circuit at all. Okay, there is no gates that we are using because G3 is equals to B3. There is a single wire. Okay, there is a single wire from input to output. You have to just connect a single wire. Although implementation part I will explain it in the laboratory session. So try to understand only the circuit diagram. Okay, how to write the circuit diagram from the expression. So now can I write this as? So can I write this G2 as? Okay, can I write this? Can I write this G2 as B3? B3 XOR B2 is nothing but this one now. B2. So can I write it like this? So therefore, copy down properly. So I can write it like this. Okay, you have to just bring down the expression from this format to this format. In the similar way, you bring this expression to this format, that is G1 is equals to B2 B1 bar plus B1 B2 bar. Next, G0 is equals to what? B1 B0 bar plus B0 B1 bar. Okay, you can bring to this format. Why I am bringing to this format? Because you have to design this particular circuit by making use of only AOI logic, that is AND, OR and NOT. Okay, you have to write the circuit by making use of only AND, OR and NOT. You should not use the XOR gates or XNOR gates. So therefore I am bringing the expression from this format to this format. Okay, so towards the left side the input should be there, and towards the right side you have to get the output. So now G3 is over. I am coming to G2. What are the things you want? You want B3, okay? You want B3 and you want B2. You want B3 and you want also B2. So B3 into B2, okay? B3 into B2, you will get one expression, and this is another expression. Both you have to add it. That is G2. That is what? G2. Understood? So B3, you are getting B3 and taking the inversion. So therefore you will be getting B3 bar here. B3 bar. So this B3 bar you have to multiply with B2, because here B3 bar is multiplied with B2 and B2 bar is multiplied with B3. Finally these two terms should be added. Okay. So that is what I am doing here. Okay. Next is what? Next I have to write it for G1, that is B2 and B1 I have to write. That is B2 and B1. Okay, B2 bar with B1. So one AND gate. B2 bar with B1 and again B1 bar with B2. Have to use one more AND gate. Finally, you can use one more OR gate to get G1. Okay. Next, you have to write the circuit for G0. So B1, B0. Okay, B1. I'm using one inverter with this. So you will be getting one. I am not going in depth because all the circuits remains the same. Okay, but only the inputs get changes. Okay, only the inputs get changes. Okay, whenever you are crossing the wire, you can use this tilt. Okay, if you are just passing like this, it means that you got short circuited. So therefore, you can make a tilt like this, and again you can make a shorted here. So it means that you are taking the point from there. Now we shall write down the numbering. whole thing. You cannot implement each and every circuit separately. You have to implement the whole thing. That is G3, G2, G1, G0. The whole thing you have to show it. Okay. So now let me write down the pin numbers. So 1, 2, 3, 4, 5, 6. Okay. If you just go through the pin configuration of the NOT gate. Okay. So there are 6 gates in one particular IC. So therefore 1, 2, 3, 4, 5, 6. Next, here 7 we are not using. 8, 9. Okay. 8, 9. Then 10, 11, 12 and 13. Okay, just go to the pin numbers whether it is correct or not by referring it to the pin configuration of the NOT gate. Okay, let me write down the pin numbers for AND gate. Okay, so 1, 2. So in one AND gate, how many in one particular IC, AND gate IC, how many AND gates will be there? So there will be 4 AND gates. So how many AND gates are there in the total circuit? 1, 2, 3, 4, 5, 6. So 6 AND gates you are using. How many ICs are required for you for this particular experiment? You require 2 ICs. You require 2 ICs of AND gate. And always remember, you should write the pin number for NOT gate. You have to write the pin number for AND gate and you have to write the pin number for OR gate here in the pencil. I am not writing it here because there is no space, and if I just keep on stuffing, if I just keep on writing there, then there will be no proper visibility. Okay. Okay. So 1, 2, 3, 4, 5, 6. Okay. 7 we are not using. 8, 9, 10, 11, 12 and 13 and 14 we are not using it. We are connecting it for some other purpose. And again, this is the 2 AND gates that we are using from the second IC. So therefore again I have to start writing 1, 2, 3, okay, 4, 5, 6. Okay, now I will start writing for OR gate. So how many OR gates will be there in one particular OR IC? So there will be 4 OR gates. But how many are using in this experiment? There are only 3 OR gates that we are using. So therefore only one IC is enough. Okay, so let me write down 1, 2, 3, 4, 5, 6, 7, 8 and 9. So this is what the numbering you have to do it. So from the first circuit diagram you are getting G3, and from the second circuit diagram you are getting G2, G1 and G0. Okay. So how to verify it and how to implement it, all those things we will see it in the laboratory session. Just copy down this much. So binary to gray explanation is done. Okay, binary to gray explanation, that is our design part is done. Implementation is still left out. So the design part is done from binary to gray, and left over is gray to binary. We'll just see a little bit later on. Okay. Copy down properly.